Hello students, in this lecture we will be deriving radius, velocity and energy of an electron using Rutherford's model. So this is the diagram of an atom in which electron is revolving with a speed of v and the centripetal force is Fc. Any electron moving in circular motion would require a centripetal force. Anything in circular motion requires a centripetal force. Now r is the radius, and here you can see the nucleus has a positive charge. And how much positive charge does it have? Plus Ze, where Z is the atomic number which represents the number of protons, and E is the charge on one proton or electron. Now we know that centripetal force is provided by electrostatic force, so we can write Fc will be equal to Fe, and we know centripetal force is mv square by r, and electrostatic force is given by Coulomb's law, k q1 q2 by r square. So q1 will be Ze, which is the charge on this proton, and q2 will be the charge on electron. Now instead of putting minus e, I have used only the positive value. Why? Because we are equating magnitude, and magnitude is always positive. So 1r gets cancelled here. mv square should be equal to k Ze square by r. Right? Now we will put the Bohr quantization condition. So it says that angular momentum, which is mvr of an electron, should always be an integral multiple of h upon 2 pi. So h upon 2 pi is that quanta of angular momentum, and n is an integer here. We also call n as principal quantum number. So from here, can we say that the value of r will be equal to nh upon 2 pi mv? Now we can plug down this value of r into this equation, and we will simply get mv square by r mv square by r, or you can say mv square will be equal to k Ze square, and we are plugging down the value of r, which is nh divided by 2 pi mv. So it will be mv square will be equal to k Ze square into 2 pi mv by nh. Right? Now 1v gets cancelled, right? So, and m will also get cancelled. So the value of v will be equal to 2 pi k Ze square upon nh. Right? Now this is the value of v, and we see that v is inversely proportional to n. So as you increase the speed, as you increase n, the speed is going to decrease. So we have found out v in terms of n. Now you will have to please pay attention, because this is going to be a longer video, because I am going to derive each and every term, like is radius, velocity and energy, and so it's going to be a longer video, so please stay connected. V is this much. Now in order to find out the value of r again in terms of n, we can just go ahead and put this value here in this equation. So r will be equal to nh divided by 2 pi m, and the value of v is 2 pi k Ze square upon nh. Now we can say that r is equal to, now nh will go in the numerator, so n square h square divided by 2 pi into 2 pi will give you 4 pi square into m k z e square. Now here you can see that radius is proportional to n square. So we say that r is dependent on n, so we put a subscript here. So radius of nth orbit is proportional to n square, which means that if you compare first and second orbit, for second orbit n will be 2, so 2 square will become 4. So second orbit is 4 times larger in radius than the first orbit. So this formula is very important, and this can be used to ask one more question, that if n is doubled, then how many times the radius is going to increase. So answer is 4 times. Here velocity is inversely proportional to n, so we also put a subscript here that velocity is dependent on n. Okay, now let us now talk in terms of energy also. So kinetic energy K. Kinetic energy K is half mv square, and we know the value of n, v. So it will be half mv square, or we can do it like this, we can make it more simpler. Let's say the kinetic energy is half mv square, and we know that mv square is this value kze square. You can see it right here, this one. So it will be half of mv square, which is from this equation, it will be k z e square upon r. Make sense? And then we'll talk about potential energy U. U is given by k q1 q2 by r. So let's plug down the values. The value of q1 is ze, as you can see here, ze, positive, and the electron has a negative charge, so minus e. Now please remember, I have not ignored negative sign here. Why? Because we are calculating potential energy, and it could be positive as well as negative. It's not a magnitude, so it comes out to be equal to k with a minus ze square upon r. Now total energy is E, which will be equal to kinetic energy plus potential energy. So kinetic energy is k ze square by 2r and minus k ze square by r. So if we take out k ze square by r common, we will get half minus 1, which will be simply E is equal to minus k ze square by 2r. Right? Now this value of energy can be represented in terms of n if we take the value of this radius and plug it right here. Okay, so let's do it. So energy E will be equal to minus k ze square by 2 into r, and the value of r is this. So we will put down the values: n square, h square upon 4 pi square m k z e square. So it solves down to, take this 4 pi square in the numerator, so 4 pi square, and there is a k here, so k multiplied by k will give you k square. So m, k will be taken in the numerator, so it becomes k square, and z also becomes z square, and e square becomes e to the power 4 divided by 2 into n square h square. Now 2 will get cancelled, so minus 2 pi square m k z square e to the power 4 divided by n square h square. So this is dependent on n, so we put a subscript here, and we see that energy of nth orbit is inversely proportional to n square. Now here comes a very important part. We know that the value of n will decide the value of energy. So n is basically the principal quantum number. So let us discuss this in detail now. This value right here will decide the value of energy in different orbits of an electron. So let us consider hydrogen atoms. So for hydrogen, we know that the value of Z, or atomic number, is equal to how much? 1. So Z is equal to 1. So energy of nth orbit will be equal to minus 2 pi square m k into e to the power 4, because Z becomes equal to 1 upon h square n square. Now if we calculate this value in joules and then we convert it into electron volts, this value comes out to be equal to 13.6 electron volt. And you know how to convert joules into electron volt, right? So this value I have pre-calculated it, so it is minus 13.6 electron volt divided by n square. So we see that energy is changing according to this equation. So if I talk about the first orbit, n will be equal to 1, so energy will be minus 13.6 volts, electron volts. Now energy of the second orbit will be equal to, we'll put the value of n as 2, so minus 13.6 divided by 4, minus 13.6 divided by 4, so it will be how much? 13.6 divided by 4, it will be minus 3.4 electron volt. Similarly, energy of the third orbit, minus 13.6 divided by, put the value of n as 3, so 3 square will be giving you 9, so 13.6 divided by 9, it is approximately 1.5 electron volt. So as you see that as we go higher and higher up the orbit, the energy is actually becoming less and less negative, right? That means energy is increasing, it is becoming less negative. So it is, energy is actually increasing. The number is decreasing, but because it is negative, the actual value is increasing. So we are going to use this very equation and we will see how it works. Just a moment. You can note it down. You can pause the video and note it down. So let me plot the energy levels inside an atom. So if we plot the energy levels, we will actually be getting something like this. This is n equal to 1, n equal to 2, n equal to 3, and we know that this level is minus 13.6 electron volt, this is minus 3.4 electron volt, this is minus 1.45 electron volt, and we know that the gap is going to decrease as we rise higher and higher. Okay, so this is the first orbit of electron, second orbit, and the third orbit. Now let us say an electron jumps from a higher orbit to a lower orbit, right? So the value of n here is, let's say, n initial, and then it jumps to n final. So the initial energy will be equal to minus 13.6 divided by n initial square, and final energy will be minus 13.6 upon n final square. Now because the electron loses energy, the loss in energy will be equal to E initial minus E final, which will be minus 13.6 by n initial square minus of minus 13.6 by n final square. So it will be equal to 13.6 into n final has a positive sign because minus minus gets you positive, so 1 by nf square minus 1 upon ni square. You can check this out how this is happening. Now we know that this difference in energy, the loss in energy, is emitted in the form of a photon. So this must be equal to, loss must be equal to h nu. So h nu will be hc by lambda. We know that frequency is speed upon wavelength. hc by lambda will be equal to 13.6 into 1 by nf square minus 1 by ni square. So from here we can get the value of lambda. So 1 by lambda will be equal to, you take this hc here, so it will become 13.6 by, it is an electron volt, divided by hc, where h is Planck's constant and c is speed of light in vacuum, 1 by nf square minus 1 by ni square. Now as you can see here, this is a constant, and we can find out the value of this constant by just plugging down the values of h and c. So if you plug down the value of h is 6.626 into 10 to the power minus 34, and speed of light in vacuum as 3 into 10 to the power 8, you will get 1.097 into 10 to the power 1.097 into 10 to the power 7, right? And it will be equal to 1 by nf square minus 1 by ni square. This value is known as Rydberg constant, represented by R. So this value is basically R. So let's now quickly summarize what this formula means. You can note it down by pausing the video now. Okay, so we have this formula. And it says that 1 by lambda is equal to Rydberg constant times 1 by n f square final orbit square minus n initial square. Now this is a very important formula. We call it Rydberg's formula. Rydberg's formula. And the value of R, as we know, how much is the value of R? Is 1.097 into 10 to the power 7, and the unit will be meter inverse, because lambda is in meters, so R will be in meter inverse. This is Rydberg constant. Now what is the significance of this equation? The significance of this equation is that if an electron jumps from initial orbit to final orbit, it will emit out a photon of wavelength lambda, which can be calculated using this formula, right? Now when you heat an atom, or when the atom is in excited state, it loses energy in the form of a photon, because electrons are actually jumping from higher orbits to lower orbits, right? So there will be a series of photons which will have different energies, so we will get a series, right? So these, we are going to discuss this series in detail right now. So let's go ahead and discuss the series. When an electron jumps from a higher orbit to a lower orbit, let's say this is the lowest most orbit, n equal to 1, this is n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, and then ultimately we will get n equal to infinity, right? Now let us see if an electron jumps from this orbit to this orbit, 2 to 1, or from 3 to 1, or from 4 to 1, we will get a series of photons, right? Or from infinity to 1 also. So such series of atoms will be called Lyman series. Such series of photons will be a part of Lyman series. So we say that in Lyman series, n final equal to 1 and n initial could be 2, 3 and so on. So in this Lyman series, all the landings are taking place on n equal to 1. So if all the landings are taking place on n equal to 2, so from 3 to 2, or from 4 to 2, or from 5 to 2, or from infinity to 2, this will form Bohr series, right? And then let's take the third one, for Bohr series, n final will be equal to 2. And then let's talk about n equal to 3. So this series in which all the landings are taking place at n equal to 3 is known as Paschen series. So Lyman, Balmer, Paschen is nf equal to 3, and then if nf equal to 4 we call it bracket series, and if nf equal to 5 we call it Fund series. P is silent here. Fund series. Okay. Now what kind of questions can be asked from these type of from this discussion? So let us say I have a question. It says, what is the highest energy present in Lyman series? Which is the highest energy photon present in Lyman series? So as you can see, in the first transition from 2 to 1, the gap is small, so the energy of this photon will be small. But for this one, as you can see, the gap is from infinity to 1, so the gap is much larger, so a higher energy photon will be emitted. So for higher energy photon to be emitted, we know that for highest energy photon, n initial will be equal to infinity, because it is jumping from infinity, and n final will be 1, so nf will be equal to 1. So we know that energy difference E initial will be 0 because n is infinity, and E final will be equal to minus 13.6 by n square. N is 1, so minus 13.6 electron volt. So what is the difference between this and this? 13.6 electron volt. So the energy of the photon will be equal to 13.6 electron volt in positive, right? You can find out this value by just subtracting E final minus, or E initial minus E final, right? So that's how you get the highest energy. So if it asks for lowest energy, then n initial will be 2 and n final will be 1. Make sense? Now it might be asked that in which of these transitions is the frequency maximum. So we know that E is equal to h nu. So the photon in which energy is maximum, the frequency will also be maximum. We also know that hc by lambda, h nu is hc by lambda, so the photon having highest energy will actually have the lowest wavelength. Why? Because it is inversely proportional, right? So let's do another question. The question says, find the least wavelength present in Balmer series. Find the least wavelength present in Balmer series. This is the question. So let's do the, we know that we want the least wavelength. Least wavelength will be present in the highest energy, because energy is hc by lambda, so least wavelength means highest energy in Balmer series. So as you can see here, this is the Balmer series. So which transition will result in highest energy? This one, because initial is infinity and final is nf equal to 2. So n initial will be infinity and n final will be equal to 2. So we can just find out the value of wavelength by using Rydberg formula. 1 by lambda is equal to r. R is 1.097 into 10 to the power 7 into 1 by nf square. Nf is 2, so 2 square minus 1 upon infinity square. 1 upon infinity square will give you 0. So from here 1.097 into 10 to the power 7 divided by 4, 1 by lambda. So lambda will be the reciprocal of this value. You can calculate it. Okay. Now on the other hand, if it asks for the maximum wavelength or the highest wavelength present in Balmer series, so for that this transition will be taken into account. Why? Because for highest wavelength the energy should be least. So this transition has the least energy in Balmer series, from n initial equal to 3 to n final equal to 2. So that's how you do questions here in atoms and nuclei. Thank you.